Hello and welcome. I'm Siyuan from USC. In the next few minutes, we will be exploring the SCEC2024 meeting poster number 12, Mapping of Absolute Deviatoric Stresses Around Two California Earthquakes Reveals a Very Weak Crust. The strength of the crust has been a long-standing question in seismology, tectonics, and geodynamics. In the present study, we try to address this issue by reconstructing the full deviatoric stress tensors using the high-quality focal mechanism catalog in ridge crust together with stress changes imposed by the two sequential mean shocks that occurred in July 2019. Figure 1 here shows the high-quality focal mechanisms we used from the hash catalog by Zhang et al. And Hodgson et al. 2012. All focal mechanisms were divided into 12 spatial blocks shown in the figure, and each block was further divided into two periods, before and after the ridge crust doublet. Rather than using all focal mechanisms in each of the 24 spatial temporal blocks, we selected the best 50 with the least uncertainties because previous synthetic tests have shown that 50 is enough for stress inversion. We treated the 12 pre-event blocks as an ensemble with the same stress conditions, which is reasonable given the absence of large earthquakes during the period. We employed the package by Cook 2014 to invert for the stress orientations and ratios, and the results are shown here in figure 2. Each block has two panels for its pre- and post-event stress orientations, and the left ones are the uniform pre-event stress orientation, which is the same as we assumed. The uniform pre-event stress orientation is consistent with the focal mechanisms of the mean shocks. We observed large stress orientations in several blocks like 2, 7, 11, and 12. Blocks 2 and 7 are close to the mean fault, so they likely to have released a substantial portion of the pre-event stresses, altering the pre-event strike slip regime to one with more normal faulting. Overall, they observed significant stress rotations in most blocks, indicate comparable levels of pre-event and co-seismic stresses. We also conducted inversions treating the pre-event blocks individually, as in the supplement of our preprint, where the stress rotations are quite consistent. The amplitude information was added further by the co-seismic stress changes, which was calculated using the Okada solution. We implemented two distinct sleep models. One is shown here by Xu et al. In 2020. The other one from Yue et al. In 2021 was plotted in our preprint. Additionally, each block should have one representative co-seismic stress changes. We tried different strategies, and the one presented here is averaging co-seismic stresses at all post-event hypocenters in each block. The second inversion is demonstrated by this equation, where the co-seismic stress change equals to the subtraction of pre-event from the post-event. The inverted maximum shear stresses are shown in figure 4. These left panels of each block denote the pre-event stresses, and they are assumed to be the same. As mentioned above, we plotted the increase of these maximum shear stresses in a map wheel. Blocks around the major faults experienced an extensive stress release, while block 8 at the terminus of the fault was loaded by the doublet. Furthermore, we conducted a pixel inversion by partitioning the study area into small pixels at 0.01 degree intervals in both directions. The pattern of the stress increase is consistent with that from the block inversion above. When looking at the amplitude of these maximum stresses, this color bar is truncated, but the maximum value is about 9.5 megapascal, which is 1 to 2 orders of magnitude smaller than predictions from Beerley's law, indicating a very weak continental crust. Elevated fluid pressure or low friction coefficient could be used to explain it. And remember that we only revealed the stress conditions in small or large fault zones because we only sampled the places where earthquakes happen. In this map, we found the highest stress near the M6.4 as well as high stress near the M7.1, suggesting the likelihood that the second larger event would be triggered by the first. Coming back to the issue we pointed out in the beginning, our study strongly supports that faults rupture seismically at very low shear stresses, reminiscent of the crustal stress model proposed by Burr and Platt in 2014, where the load-bearing layer is the ductile middle crust and the brittle upper crust is weak. Welcome to stop by our poster and read our preprint using the link for more details. Thank you for your attention.